So we've completed our graphs in section 6.3 on exponential functions, and now we want to look at exponential equations. This is the last thing we'll do. So let's look here where it says solving exponential equations. Now that we know what an exponential function is, let's learn about how we can solve exponential equations. For example, how would you solve the following? So we have 5 raised to the x plus 3 power, and that's equal to 1/5. So what is x? Well, we might notice that 1 over 5, can be written another way. We could write this as 5 to the x plus 3 power equals 5 to the negative 1. Isn't that the same as 1 over 5? 5 to the negative 1 equals 1 over 5 to the positive 1. Well, now we can see that if 5 raised to x plus 3 is the same as 5 raised to the negative 1, then we should be able to conclude that x plus 3 equals negative 1, and indeed we can. We subtract 3, and we get x equals negative 4. We can check, go back and plug in negative 4 for x. You end up getting 5 to the negative 1 equals 1/5, and of course that checks. So our solution set is negative 4. So what makes this equation different from equations we've seen before? Well, we now have the variable in the exponent. Variable in the exponent. So we have to come up with techniques for isolating that variable x. Okay, so just here's one way we can solve exponential equations. If we can write it like this, if a to the u power equals a to the v power, then what did we just see was true? We saw that u is equal to v. We said if the powers are equal and the base is the same, it's not a to the u equals b to the v. The base has to be the same. This means if you have the same basis on both sides of the equal sign, you set the exponents equal. The key here is to manipulate as needed so that the base is the same. So it won't always start that way. Here we had to do a little bit of work before we had a to the u equals a to the v. Now, every exponential equation cannot be solved this way, but if we can write it with the same base, that's what you want to do because it's easier. The technique is easier. Okay, let's look at example 8, part A. The question being, if we've got 2 to the 3x minus 1 equals 32, can we write 32 with a base of 2? Well, play around with your calculator a minute. 2 to the 3rd power, 2 to the 4th power, 2 to the 5th power, and you find 2 to the 5th power is indeed 32. So we rewrite 32 as 2 to the 5th, and now we have a to the u equals a to the v, so u equals v. And solve for x. Add 1, divide by 3. And our solution set is 2. And indeed, you can plug that in and check. Part B is already in that format, isn't it? We already have a to the u equals a to the v, so u equals v. That one was simple. Part C, 4 to the 2x minus 5 equals 1 over 16. So the question is, first, can we write 16 with a base of 4? Yes, we can. That's 4 squared. And 1 over 4 squared is the same as 4 to the negative 2 power. So we have a to the u equals a to the v, so u, 2x minus 5, is equal to v, negative 2. Okay, so add 5 to both sides, 2x equals 3, divide both sides by 2, x equals 3 halves. No decimals, remember. We want fractions in lowest terms, improper if necessary. No mixed numbers. All right, part D. Here again, we have 2 to the 2x minus 1, and we know we can write 4 as 2 squared. So 2x minus 1 equals 2. Add 1, 2x equals 3, divide by 2, and we get 3 halves for this one also.